So we're going to work with two data sets that we have seen before, the concentric circle and binary blobs. The concentric ones, this one is much nicer, let's say, because there's a larger gap between the two classes. All right. So we're going to build a neural network that has multiple layers. Okay. So each layer is going to take an input and provide an output. The input dimension, output dimension are not necessarily the same. And in the network, we have two cycles. We have the forward pass, or the forward cycle, and the backward cycle. So for the forward, we're just computing the output of each layer. And in the backward, we'll be trying to find what is the derivative of the loss function with respect to each layer parameters, okay? And to do that, we're going to use a chain rule. So there are so many multiple colors here, but let's start with the blue one, okay? We have a layer F followed by a loss. So you can imagine this is a very simple neural network. There's one layer followed by the loss. So we have X, it's d-dimensional, and this layer will output Z, which is q-dimensional, okay? Once we do that, the loss function will compute some loss between Z and the true labels, which is Y, okay? So Z and Y are in the same space. Both of them have dimension Q. For simplicity, you can imagine Q is 1, okay? So let's say we're doing some regression problem on one dimension, or we're doing classification problem for binary classification. So Z there is going to be something either 0 or 1 or something between 0 and 1, okay? So X here, you can see it as X train, and Y here is Y train, okay? We transform X train by using layer F. We get Z, and we compute, for example, the mean squared error between Z and Y. And that will provide us the loss, the value of the loss. Perfect. Now, you can imagine F is a simple perceptron that has coefficients W and intercept V. And we want to use stochastic gradient descent to optimize W and V in this neural network, okay? So the first thing we need is what is the derivative of the loss with respect to Z, okay? If we compute the derivative of the loss with respect to Z, it basically tells us at which direction should we push the output Z to minimize the loss, okay? So this is what we need. This is the first derivative that we need, okay? So this first derivative would tell us in what direction should we push the output of layer F. Perfect. Once we have that, we're going to optimize the parameter of F called theta using the chain rule. And the chain rule tells us that the direction following which we should change theta is simply some sort of product, depending on the space we're working on, between the derivative of the loss with respect to Z multiplied by the derivative of Z with respect to theta. All right? And if you've done physics, you've seen people just simplify these two, right? You can just simplify them, and then, let's say, logically, you will get derivative with L with respect something like this, okay? So this is the direction at which you push. Analytically, it's not always correct, but let's say in physics you can do that if you're at a certain position, okay? Once we optimize, all right, so this gradient here is the gradient that we'll be using to update theta. Perfect. Now, imagine I have another layer here called like G. It's the same thing, okay? So imagine like we're not having X. X comes from another layer. We're just going to apply the same logic we applied on F. We're going to apply it on G, right? Because X here will be the output of G. We have the derivative of L with respect to the output of G. Perfect. Can someone guess what is this? What's the expression of L with respect to X? We're going to use the same thing. We need, it's the derivative of Z with respect to X, the derivative of L with respect to Z. This one is given by the previous layer. We have to compute that and send it back to G. So now the derivative with respect to X plays the role of this thing. So in the code, we'll be calling this grad output of F. Okay? This is grad output of F. This is the grad parameter, and this is the grad input. If there's another layer, grad input of F is going to be grad output of the other layer. So it's kind of a recursive. So I hope this is clear now. It's not magic. Good? So here, just the write-up of what I just explained. We can assume that the loss is the mean squared error. Okay? So this is the LYZ. And the derivative of the mean squared error with respect to Z is going to be this one. Okay? So there's an error here because that's just the derivative with respect to one sample. Okay? So the notation here is L of Y Z. This is basically, you can imagine, this is Y1, Y2, all the way to Ym. And this is Z1 all the way to Zm. Okay? So we start with this simple one. We given Y pred and Y true. So Y true is Yi, Y prediction is the Z here. And we're going to just implement the forward pass of this function. So in the forward pass, I'm given Y true, Y pred, and the MSE will simply be Y pred minus Y true. Okay, I'm going to just apply the square and then compute the mean. Okay, so it's going to be okay. There is one thing in the backward pass. In the backward pass, we don't provide any arguments. Okay, so each forward pass is followed by a backward pass. If I go to the formula of the gradient, so the input, if the input is Z, then the gradient is 2 by M Z minus Y. Y here is the Y true, and Z is Y pred. The problem in the backward pass, I'm not provided anything. So in the forward pass, I have to keep track of these two quantities because I need them to compute the gradient later. Make sense? No? In the forward pass, I'm giving the input Y and Z, and I compute the loss. In the backward pass, we will see we're not provided anything as input. So to compute this, we have to keep track of Z and Y for the gradient. And this is what the attribute saved arrays is for. In saved arrays, after each forward pass, we're going to save the quantities that we will need to compute the gradients. Okay? You see the backward method does not have any input. So we have to keep track of things. Once the backward pass is done, the saved arrays is reset. Okay? So here when I do the forward, I'll just try to save. I'll do self-saved arrays. And I'm going to put Y pred, Y true. Okay. Now in the backward pass, I'm just going to recover these from saved arrays. And the grad input for the loss is just going to be what we just seen there. I'm going to call it grad input equals 2 multiplied by ypred minus y true, and then I have to divide by m, so in this case it's just ypred shape 0. So it's the number of samples that we have. Okay. So for the loss now, we have how to compute the loss and then how to compute the derivative of the loss with respect to the prediction. So I already did multiplied by mean, but yeah, so let's see here. I didn't divide. Okay, so it's 1 over m. Let's do it manually. Let's do sum divided by okay. Yeah, I guess there's a problem with the mean. All right. These are just sanity checks to make sure we're doing things correct. Okay. So now we're going to move to some other layers. You have seen activation functions. Okay. So we're starting with the nice layers. So we have the loss because there's no parameter. We're going to do the same thing with activation functions because there's no parameters for activation functions. So grad input is much easier to compute when we do the backward pass. Okay. This is just a skeleton of the layer class that we're going to use, but basically we have the sigmoid, and then we're going to use also ReLU, right? So if you remember from logistic regression, the derivative of sigmoid with respect to the input is basically sigmoid multiplied by 1 minus sigmoid. So this is what we're going to use for the backward pass. So the forward pass, simple sigmoid equals 1 divided by 1 plus pexp. That will going to be minus x. Okay. For the backward pass, I need this quantity here, so I'm just going to save it. So in self saved arrays, I'm just going to put sigmoid. Okay. In the backward pass, I have the grad input, and the chain rule will be the same. I'm going to take L, so I basically want to compute this, right? This is given, this is the grad output in that method, and this is the derivative of the output with respect to the input, so this is basically sigma of 1 minus sigma. Makes sense, the chain rule? Okay. This is an element-wise operation. As you've seen here, we applied the sigmoid on element-wise, okay? So basically, the input of the layer has the same dimension as the output of the layer. We're not changing any dimension, okay? So in this case, grad input is going to be sigmoid multiplied by 1 minus sigmoid multiplied by grad output. There's one thing here we usually do in neural nets, in deep learning. We want to clip this thing, so we don't want it to explode. So usually we do NP clip of x between minus 25 and 25. You don't have to do it, but usually you want to make sure that if x is too large, you're not going to have an issue. This only happens when you're just starting training, because depending on the weights, you might get some large values. So the ReLU, you have multiple ways to do it. If people who don't know what ReLU is, would just do okay. So if x is less than 0, you clip it, we just return 0. If it is positive, we just keep the same value. So you can do ReLU, you can do clip, x between 0, I think this, or you can do basically x multiplied by x greater, okay. It's as simple as that. And the derivative of this function is going to be 1 if x is greater than 0 and 0 otherwise. So we just have to return 1. And this basically I need to save self-saved arrays. I'm going to only need x. Okay. And I can just do grad input equals grad output multiplied by the derivative. In this case, we said it's x, or basically what I call self-saved arrays. So sigmoid passes, ReLU passes. We're doing great. All right, so we're done with the loss layer. We're done with 2 activation functions layers. We're going to move to basically a linear layer. We can call it linear layer, or basically the basic layer of a multi-layer perceptron, or just a perceptron. Okay, just XW plus B. So you don't have to do the math. The derivatives are provided, right? Delta fx is the derivative of the output with respect to the input, and everything is given there. So we're going to use this to get these two to get their parameters gradients, and these two to get the grad input. Okay. One thing you have to note, or basically if you want to implement this question, the only thing you have to be careful about is the shape. The shape of the solution is everything you need to figure out should I multiply on left or right and stuff like that. Okay. But before that, we're going to use a simple modification of NumPy arrays to represent W and B. Okay, this is an imitation of PyTorch. So we're going to add an attribute called gradient, where we're going to store the gradient of W and the gradient of B, just to make things simple. Okay. So this parameter here, class here, you can just see it as a NumPy array. The only difference is I provide a NumPy array is going to have a value, the initial value. In this case, is going to be once. It's going to have a name that I provided. I don't have to. The gradient, initial gradient, is going to be 0, but I can always change the gradient. Okay. And they have apply gradient and 0 gradient. So 0 gradient, we're just going to set the gradient to 0. Apply gradient is going to subtract the arguments that I provide from the parameters. Okay. So this cell just shows you how this class is used. I have defined. All right. Yeah. So the ID here is basically the memory ID from Python. Okay. So why I do this is just to show you that if I use apply gradients and 0 gradients, it's the same object, okay? But if I do, W equals like W minus like 2A or something, this W now is going to have a different memory ID, okay? It's not going to be the same object. Yeah, we're going to use it, so you're going to see later how we're going to use it. It's much simpler than it looks. But let's start with the dense layer, which is basically the perceptron layer. All right? So the forward pass is much easier. One thing to note here is that the bias has shape 1 output dimension. Okay? So we call it Q, basically. And the weights is going to have shape input dimension, output dimension, so it's going to be dq, basically. And x here, so input dimension is basically d, and I want to return something that has shape mq. Okay? So the output, I'm just going to do x dot self weights, right? Plus self bias. Not use this layout, okay. All right, so this is the forward pass. So now we have to look at the gradients and see what the quantities that we need, right? So the only quantity that we need to keep track of is x, because W is saved in self weights, so we don't need these, but we need to keep track of the input to compute the gradient in the backward pass. So here I'm going to do self saved arrays, which is going to be x. Perfect. All right, so now let's see how to compute the weights parameter. Okay, so we're just going to use the gradient argument here. We're going to use the same way we did here. W gradient, we're going to set the gradient. Sorry, where I was. I was here. Okay. So I'm going to do self dot weights dot gradient. As I said, you only have to rely on the shape of these quantities to find which one you should do. So we have the derivative of the output with respect to W is x, and the derivative of the loss with respect to the output is grad output. Okay, so grad output has shape m output dimension, which is basically mq. X has shape MD, and the gradient has the same shape as W, so it was dq. Okay? So I would simply do X dot transpose and multiply by grad output. Now I can move to the gradient of B, which is basically the ones array, and then I'll multiply the grad output. So you have multiple ways to do it. We can just imitate the formula, not doing anything fancy. I can just do self dot bias dot gradient. Okay, grad output is M by Q. Okay, so I can just do grad output. I need to get something that has shape 1Q. Okay, so I can just do grad output dot transpose, and then I can do at MP1s. And here is going to be X dot shape M. Shape 0. So that's the number of samples that I'm getting in. Yeah. I can do differently, which is much easier. I can just do sum. I'm multiplying by ones, which means that I'm just summing. So I can do NP, just do NP sum. And then here I'm going to have grad output. And I'm summing with respect to the first axis. And I want this gradient to have the same shape as bias, which is 1Q. I can do keep dim equal true, if I'm not mistaken. So the next thing I need is the grad input. So the derivative of the output with respect to the input is W. So in this case, I need W, and then I'm multiplying the grad output. Okay. So I want grad input in this case to be MD. Okay. Grad output is MQ. So I'm just gonna multiply by the transpose of the weights. So it's going to be self weights, then transpose. Okay, so this is basically MQ at QD. So it's going to be MD. Okay. So in this question, you don't have to do any math. You just have to do some common sense to figure out the formulas. Let's see if they work. So we have set the gradients in weights, we have the set gradient bias, and we have computed the grad input, which is the derivative of the loss with respect to the layer input. Okay, have a problem in, okay. Keep dim is in PyTorch. Keep dims, okay. But there's an underscore, no? Okay. All right, we're good. We're doing good. This was a grad level homework before. Doing fine. All right. So now we're gonna implement what we call SGD, which is kind of optimizer. We have seen SGD before. Just you're gonna go to the parameters and then apply the gradients. Okay. So the SGD, we have a learning rate. We have the layers. So each layer has parameters. Okay. So each of those layers, where are they? So yeah, so each of these layers has parameters. We have seen that the activations, they have, there you go. So for the, by default, parameters is empty. So the activations, they don't have parameters, so the list is going to be empty. For the perceptron layer, we have the parameters is the bias and weights, okay? So everything we're going to do is going through the layers, look at the parameters, and then apply the gradient. Once we do that, you can just zero out the gradient. So I'm just going to copy this, okay? I'm too lazy. And this is what I'm going to do, okay? So we're going to go through the layers that we have for layer, for layer in self layers, and then I'm going to do for W in layer dash parameters. Copy paste, but the learning rate in this case, it is self learning rate. Okay. Now we want to put all of these things together, the loss, the activation functions, the perceptron layer, and the optimizer, in one thing, and that's what we're going to call the network, okay? So at the network, we're going to provide the optimizer and the loss, and then we're going to try to add the layers later, okay? So the forward pass, as I said, is just a recursive thing. The output of the layer is the output of the last layer, so you start from the first layer and then forward pass, okay? So in this case, just going to do for layer in self layers, for layer in self layers, output equals layer dot forward of output. It's as simple as that. For the backward, on the other hand, first thing we need the derivative of the loss with respect to the input. So once we get that, then we go the same thing, step by step, but backwards. We start from the last layer and we go all the way to the final layer. Okay? So we get the first grad output from the loss. That's where we computed the 2 multiplying the difference of the prediction and the true labels. And now we're going to go backwards. So we're going to do for layer. There's multiple ways to do it. I like to do it this way. It's much more concise. Okay? When you do this, it means that you're going backwards. Okay? And in this case, we're going to do grad output is going to be layer that, backward of grad output. The theory is much more complex than implementation. As you see, just understanding those chain rules and which one you're going to multiply and which one you shouldn't. But once you do that, everything just works very easily. All right, so we have the grad output from the loss. Then we go for the layer in self layers. We computed the backward pass. So during the backward pass, what happens is that all the parameters, the gradient of all the parameters is set, so it's not 0. Okay? And all we have to do now is simply to apply the gradients. Okay? So that's what happens in the fit batch. So the loss here is going to be self loss between the true and, So we're going to compute the loss, which is in this case the loss forward between the y. I always mix these. Is it y pred, y true, or y true, y pred? Let me see. Okay, it's y pred, y true, so we can work on that one. So now if we go to the network, we just apply everything we have seen so far, compute the loss, which is forward. So y pred here is what we call output, and the true one is batch y, okay? So now I have the loss. Now, basically I have the forward pass. I can now do self backward. And now I'm gonna call the optimizer apply gradients, okay? In the backward pass, all the parameters gradients are set. So now just do self optimizer apply gradients. If you use PyTorch, it's a step, a forward optimizer step, something like that. Okay. The fit method is provided. This is just shuffles the data and does a stochastic batch gradient descent. It's very similar to what you've seen in logistic regression. Let's see if everything works. Looks good so far. So here I just provided the layers. This is a simple neural network. Provide the SGD, the loss is going to be MSE. Then we start with dense, followed by ReLU, dense, followed by ReLU, and vice versa. And the final one is going to be sigmoid. So basically, we're basically training a logistic regression, but it's not a simple linear regression. We have a stack of nonlinear activations, okay? If you want a simple, like if you want something equivalent to logistic regression, you can just do this. You can just remove all of these, right? And then you're just going to do 2 by 1, something like that. But here we have multiple layers. So the output will be sigmoid, which is the probability that the predicted class is 1, okay? And we're going to cheat a little bit. We're not going to use the log loss or the cross-entropy loss they usually use to probabilities. We're just going to use MSE. So we want the sigmoid values to be close to the true labels, okay? It's not mathematically sound, but just to show you what happens. So what happens here is that we're going to train for 50 epochs. The learning rate is already set in stochastic gradient descent, 0.1. And at the end of each epoch, I just want to plot the decision surface to see how things change when I'm trained in neural net. It's going to take some while, okay? So I start around 0.25 MSE, and I go all the way to 0.05. This is the final, sorry, this is the final decision surface. It's magic, you see? There you go, it stabilizes around the training data. Perfect. One thing you see here is that, yeah, you have a period here where the improvement is not that drastic, but once we get a certain region, we just converge to, I'm not sure it's the global optimum, but it's a good optimum, okay? Because SGD is very, what are you going to say? It's agnostic to the change or the volatility of the parameters. So in this homework, or basically in this labs, I added a question. It's 11. This is a bonus one. You don't have to do it. But if you do it and you have missed one of the previous hands-on, you get basically a second, like a opportunity to catch up, okay? So in this one, instead of applying the gradients, we are computing a moving average of the gradients throughout at each batch. We have a gradient. So instead of applying the gradient I have now, I compute a moving average of the previous gradients and apply those. Okay? So it's, yeah. So V here is kind of velocity, the speed at which the gradients are changing. M is the moving average, okay? And you're basically applying a smooth, you will have to apply a smooth out or a smoothed version of the gradient. So we're multiplying here by a kind of variance. So if the variance is high, we are reducing the norm of the gradient, okay? But that's basically the idea. If you heard Adam before, adaptive moment estimation, just taking gradient, computing a moving average, and then trying to scale by the variance to reduce that volatility. And that's why I think the reason we see that plateau at the beginning of SGD, because initially the gradient will be large because we are far from the optimal, so the gradient, the parameters will just move kind of erratically as we have seen in the previous lab. Okay? But you don't have to do that. For this lab, you just have to do the same thing for the other data set, which is the binary blobs that we have seen all the way up. The catch there, or the catch here, is that you'll have to tweak the learning rate. Okay, it's not going to work the same way for this data set. So, and then you can try use a different neural network. So that's the question that I'll be leaving for you for this participation point, okay? I basically answered almost everything here. For those who want to suffer a little bit over the weekend or just curious, you can do this. I had some students before complain that they don't understand what's happening. You can always go to the original paper. The link is provided here. And yeah, that's pretty much it. A hint here, you can use the argument name. Or the same way we did the parameters, you can use add attributes to the parameters for the moment and for the moving average and then for the velocity. Other than that, nothing special. So what I promise you get from Adam is that you're going to see that the convergence is much faster. So you're going to get something like exponentially optimal. Well, basically converges kind of exponentially instead of logarithmic at the beginning, yeah. All right, any questions? Yes?
Can you go back to the ReLU, use the backward?
Yes.
So is that where you just take the, you just take the weights and multiply by the saved rate? No,
yeah. So this is just X. The batch update or fit match?
For fit match.
Okay. Yes. So here I'm computing the output of the neural net. I'm computing the loss, which is the MSE. I need to do the forward because that's where I save the quantities for the backwards, okay? So the layers already have a forward call here. So I'm ready to compute the backwards. But for the loss, I still need to forward. Once I do that, everything follows. I'm calling backwards, which is broken down here. And yeah, this basically says I'm looping from the last layer all the way to the first layer. Okay? After the backward call, all the parameters have the gradient set. So now I just call optimizer apply gradients. Okay? Yeah. You have to basically run the code for the network to see what's happened, but in add layers, I'm accumulating all the layers that I'm adding here, and yeah, optimizer set layers. So the lists in Python are passed by reference, not by value. So if I pass the list while it's empty, if I add elements, optimizer will still access the elements of layers, so that's not an issue. The only problem you have to be careful when you add layers is that the dimension of the output of the previous layer should match the dimension of the input of the next layer. Otherwise, you're going to have some errors there. Okay? ReLU activations, they don't change dimensions because they are applied element-wise. Yeah. I get a lot of complaints in FCQ about me being fast, but I have only 15 minutes to cover everything, so I try to just cycle as much as I can. You can always go back to the lecture recordings and see what happens there. If I'm too fast or something is not clear, you can just post the question on Piazza. All right, so now you know how to do deep learning with NumPy from scratch. Congrats. I guess if you want to do advanced things, you can either take deep learning class, or I'm going to post for the Kaggle competition, I'm going to provide some basic notebooks that use Keras, so you can start from there and play with it. And yeah, yes.
So you can help office hours from 4:15?
1 second just to check. So from 4:15 until 5:15, the link is on Piazza. The Zoom link is on Piazza. Yeah.
For me, that's a big deal.